Hello everyone. This is lecture 4 of the subject analog circuits, and in this lecture I am going to discuss about active filters, the basics of active filters, the difference between passive and active filters, types of active filters and advantages of active filters over passive filters. Contents are introduction, types of active filters and the frequency response of different active filters. So starting with the filters. Basically, filters are the circuits which passes a particular band of frequency and blocks a particular band of frequency. So, whatever frequency we require, we can get those frequencies, and whatever frequency we don't require, we can reject those frequencies. Like if a particular range of frequencies are having noise, so we can reject those frequencies, right? So, basically, these filters are classified into mainly two parts, active and passive filters. As far as passive filters are concerned, passive filters, it utilizes only passive elements to design the filter. Means in passive filters, we only use resistor, capacitor and inductor. There is no active element involved in passive filter. That's why passive filter cannot amplify the signal, and in passive filters there is attenuation also, because passive elements cannot amplify the signal. That is the problem with the passive filters. But in passive filters, since we can use inductors easily, so it can be used for high frequency applications also. And as far as active filters are concerned, active filter means it utilizes active element. Active element, for example, transistor, for example, op-amp, that is made up of transistors. But along with op-amp, we use resistor and capacitor also, but obviously in active filters, op-amp will be there. This is the basic difference between passive and active filter. In passive filter, we use only passive elements, but in active filter, we use active element, for example, op-amp, along with resistor and capacitor. Advantages of active filters. As I have mentioned that in passive filters, we get the attenuation. Why? Because in passive filters, we are using only resistor, capacitor and inductor, and these elements cannot amplify the signal. So, in order to minimize, in order to remove the drawbacks of the passive filters, we use active filters, and the first advantage of active filter is it provides gain. It provides gain because we are using operational amplifier. That's why it provides gain. And another advantage of active filters, that advantage is no loading effect. Basically, loading effect exists when we apply the input signal and the circuit is having low input resistance. That's why there is a loading effect, right? So, in order to remove the loading effect in active filters, we prefer non-inverting configuration, because the input resistance of non-inverting configuration is higher. That's why you will see that in mostly circuits, in mostly active filter circuits, we will be using non-inverting configuration. So, by using non-inverting configuration, this loading effect we are going to minimize. So, these are the two main advantages of active filters. And as far as limitation of active filter is concerned, basically there is one limitation of active filter. That limitation is, since we are using operational amplifier as an active element in the active filter, so the drawback of op-amp, it will also be the drawback of active filters. And that drawback means the bandwidth and the slew rate of op-amp is limited. The bandwidth and slew rate of op-amp is limited. If the bandwidth and slew rate are limited for op-amp, then it will also be limited for the active filters in which we are going to use this op-amp. Let's take an example. There are various op-amp ICs are available in the market, and one of the popular IC is 741 IC. For 741 IC, the gain bandwidth product is 1 megahertz and the slew rate is 0.63 volt per microsecond. So you can see that the gain bandwidth product is limited to 1 megahertz. The slew rate is also not good, right? So if slew rate and bandwidth are limited for 741 IC, it means that if we design any active filter with the help of 741 IC, so those limitations will be there also. That is the issue. That is the issue of active filters, and that issue arises because of the limited bandwidth and limited slew rate of the operational amplifier. Now coming to the types of active filters, there are 4 main types of active filter. The first one is low pass filter, then high pass filter, band pass filter, band reject or band stop filter. Apart from these 4 filters, there are 2 more filters. One is all pass filter. As I have mentioned that filter is a circuit which is used to pass a particular band of frequency and rejects the remaining frequencies, right? But in all pass filter, which I have not mentioned here, in all pass filter, all frequencies are passed, but it is called filter. Basically in all pass filter, it compensates the phase, it changes the phase of the signal, and it is basically used in transmission lines. And another type of filter, active filter, is that is called universal filter. With the help of universal filters, we can implement any filter like low pass, high pass, band pass and band reject. In this class, I am just going to discuss the basics of these 4 filters with frequency responses. And as per the syllabus of analog circuits, you need to focus on the first order and second order filters. Firstly, first order low pass and second order low pass filter. Similarly, in high pass filters, there are 2 cases, first order and second order high pass filter. And in band pass filter, there are 2 cases. One is wide band pass filter and the another one is narrow band pass filter. Similarly, in band reject filters, there are 2 categories. The first one is wide band reject filter and the second one is narrow band reject filters, right? So here I am just going to discuss the frequency response of these filters. So starting with the low pass filter. So low pass filter, as the name suggests, it passes the low frequency signal and rejects the high frequency signal. When we say that the filter is passing a particular frequency, it means that in that range the filter is providing gain. And when we are saying that that filter is rejecting some frequency, it means that that filter is attenuating those signals. Attenuation means gain is very less. If gain is less than 1, then attenuation will occur, right? So when we draw the frequency response of any filter, so in that frequency response, on x-axis there is a frequency and at y-axis there is a voltage gain in dB. So that voltage gain is, let's say, V0 upon Vin mod, and in dB, convert this ratio into dB, it will be 20 log mod V0 upon V. So the frequency response for low pass filter is, it passes the low frequencies and rejects the high frequency. So you can see that we are getting this maximum gain. Let's say this maximum gain is AF, right? And there is a very important term involved in filters, that is called cutoff frequency. That cutoff frequency, it is also called minus 3 dB frequency. Let's say the cutoff frequency of low pass filter is FH. So this cutoff frequency is also called minus 3 dB frequency, it is also called brick frequency, it is also called corner frequency. So minus 3 dB frequency or cutoff frequency is the frequency at which the gain is reduced by 3 dB of the maximum gain, right? And this, there are 2 bands also, this is pass band and this one is stop band. So these names are given. You can understand that in the pass band, we are getting higher gain, the signal is passing, and in the stop band, the gain is very less, signal is getting attenuated. That's why it is called stop band. And there is one more important term, that is called roll-off rate. Roll-off rate is defined as the rate at which the gain is increasing or decreasing. For example, you can see that here the gain is decreasing. So the roll-off rate of this filter, it will be negative, of course, negative. And what will be the roll-off rate? It will be decided by the order of the low pass filter, by the order. For example, if it is the first order low pass filter, then the roll-off rate, it will be minus 20 dB per decade. If it is second order low pass filter, then the roll-off rate will be minus 40 dB per decade. If it is third order low pass filter, the roll-off rate will be minus 60 dB per decade. Or we can say that roll-off rate is basically minus n into 20 dB per decade, where n is the order of the filter. But here you need to focus on first order and second order filter only, because once you understand first and second order filter, you can design higher order filters. Because to design higher order filter, you simply cascade the first order and second order filter. For example, if we need third order low pass filter, for that we cascade first order low pass and second order low pass simply. Fine. So this is the frequency response and this is the practical response. If we go for ideal response, then the ideal response will be like this. Now you can see that this one is pass band, this one is stop band, and in the stop band there is no signal. So this is the ideal characteristics. Fine. So this is about the frequency response of low pass filter. Now coming to the high pass filter. High pass filter is a filter which passes high frequency signals and rejects low frequency signals, as the name suggests, high pass filter. So again, we are going to draw the frequency response of the high pass filter. So in high pass filter, frequency response, on x-axis there is a frequency, and at y-axis there is a voltage gain in dB. That voltage gain is mod V naught upon V. It is in dB. So the response of the high pass filter will be like this. Now you can see that the low frequency signals are getting attenuated and the high frequency signals are passed. Passing means we are getting the gain, and stopping means the signal is getting attenuated. Right? Again, there is a cutoff frequency of this high pass filter. Let's say this cutoff frequency is FL, and this cutoff frequency is basically, it is also called minus 3 dB frequency, corner frequency, or break frequency. Again, the maximum gain is, let's say that maximum gain is pass band gain AF. This one is pass band and this one is stop band. You can see that in pass band we are getting more gain, in stop band the gain is very less, right? So again, this minus 3 dB frequency you can define. It is the frequency at which the gain is reduced by 3 dB of the maximum gain, right? Again, there is a roll-off rate, and the roll-off rate for this high pass filter, it again depends upon the order of the high pass filter. If it is the first order high pass filter, then the roll-off rate, you can see that if you are coming from origin, then the gain is initially in fact increasing. You will see that it is increasing. So the roll-off rate is plus 20 dB per decade for first order high pass filter, and for second order high pass filter it will be plus 20 dB per decade. This is the roll-off rate for high pass filter, right? So this is the practical response. Similarly, you can draw the ideal response for high pass filter. Now coming to the next filter, that is the band pass filter. As the name suggests, it passes a particular band of frequency and rejects the remaining frequencies. So band pass filters are of two types. The first one is wide band pass filter and the second one is narrow band pass filter. As the name suggests, wide band pass filter, it passes wide band of frequencies. Narrow band pass filter means it passes narrow band of frequencies. There is one classification that is based on quality factor. and that quality factor Q, that is equal to center frequency FC upon bandwidth, right? So for wide band pass filter, the bandwidth is higher, so quality factor will be less. And for narrow band pass filter, vice versa. In narrow band pass filter, bandwidth will be less, so the quality factor will be more. So there is one classification on the basis of quality factor. That classification is if quality factor Q is less than 10, then it will be considered as a wide band pass filter. If it is Q is greater than 10, then it will be considered as narrow band pass filter, right? So the frequency response of band pass filter, we need to understand it. On x-axis there is a frequency, at y-axis there is a voltage gain in dB, and the frequency response is this one. Now you can see that a particular band of frequency is passing and the remaining frequencies are getting rejected. And in band pass filter there are two cutoff frequencies. One is called lower cutoff frequency, let's say it is FL, and the another one is called upper cutoff frequency, let's say this is FH, FL and FH. And the maximum gain, you can see that this maximum gain is AF. And this FL, that is lower minus 3 dB frequency, FH is upper minus 3 dB frequency, right? And the bandwidth of this wide band pass filter or narrow band pass filter, the bandwidth will be equal to FH minus FL, FH minus FL. And the center frequency, that is FC, the center frequency FC is equal to under root FH into FL, FH into FL. So here, this one is the pass band, this one is stop band, this one is stop band. Now the roll off rate is here, it is plus 20 dB per decade, and this one is minus 20 dB per decade. And the minimum order required for band pass filter is 2. We cannot design single order first order band pass filter. Minimum order requirement is 2, because at least 2 poles are required to design band pass filter. You can understand that one pole gives minus 20 dB per decade, fine. So from there you can understand that if we are going to design band pass filter, the minimum order required is 2. So one thing which I want to mention here, this band pass filter, especially wide band pass filter, you can design it with the help of first order high pass and first order low pass filter. Now you can see that this portion, it is the frequency response of first order high pass filter, and this is the frequency response of first order low pass filter. So you can design wide band pass filter by cascading the first order high pass filter and first order low pass filter. By cascading first order high pass and first order low pass filter, you can design wide band pass filter. Now coming to the next filter, that is band reject filter. So as the name suggests, it rejects a particular band of frequencies and passes the remaining frequencies. It is also called band stop filter. It is also called band elimination filter. Again, there are two types of band reject filter. The first one is wide band reject filter. Then the second one is narrow band reject filter. And the narrow band reject filter, it is also called notch filter. Basically, notch filter is the filter to reject a single frequency. It is especially used in power supplies, right? So again, we need to understand this frequency response for wide band reject filter. On x-axis there is a frequency, at y-axis it is voltage gain in dB. The frequency response, it is like this one. Now you can see that this one is stop band, this one is pass band, this one is pass band. Again, there are two cutoff frequencies in band reject filter. The first one is FH and the second one is FL. FH and FL, and FH and FL are the minus 3 dB frequencies, upper and lower minus 3 dB frequencies, right? So here one thing to note, That note is, in band pass filter, you can see that FH is greater than FL, and this FH is the cutoff frequency of low pass filter and FL is the cutoff frequency of high pass filter. These are the notations which we have taken. Like we can see that in low pass filter we have taken the cutoff frequency of FH, and in high pass we have taken the cutoff frequency FL. So in band pass filter you can see that FH is greater than FL, but in band reject filter you can see FL is greater than FH. This is very important thing, right? So in the design numericals, if FL and FH are given, so from there you can understand that which kind of filter it is, band pass or band reject filter, right? So again, this wide band reject filter, it can be designed with the help of first order high pass filter and first order low pass filter. So to design band reject filter, we simply take first order high pass filter and first order low pass filter, and just we add the output of first order low pass and first order high pass with the help of adder circuit. So to design this wide band reject filter, we will be requiring 3 op-amps. One op-amp is used to design the first order low pass filter, and the second op-amp it will be used to design first order high pass filter, and the third op-amp will act as a adder circuit. That adder circuit is basically the summing amplifier. And as far as this notch filter is concerned, normally notch filters are designed with the help of twin T network. With the help of twin T network, we can reject a single frequency, right? So this is about band reject filter. And as far as all pass filter is concerned, all pass filter, it passes all the frequencies, but it changes the phase, and it is especially used in transmission lines. For example, if any signal it moves through the transmission line, during the moment some phase is changes for that signal, and in order to compensate that phase we use all pass filter. And a universal filter, it consists of all filters, low pass, high pass, band pass and band reject filters in universal filters, right? So as far as low pass and high pass filters are concerned, like I have already mentioned that we need to study the 2 types of low pass filter. One is first order and second order. Basically, the order of the filter is determined by the number of RC sections. If we are using one RC section, it is called first order low pass. If we are using 2 RC sections, it is called second order low pass. Similarly, in high pass also, 1 RC section first order, 2 RC section second order, 3 RC sections third order. But normally when we go beyond second order filters like third order, fourth order, we can simply design the third and fourth order or higher order filters by cascading first and second order filters. That's why to study first order and second order filters are very important, because by cascading first and second order filters we can design higher order filters. Now coming to the higher order filters, one thing I want to mention here is, with the help of frequency response, on x-axis there is a frequency, at y-axis it is a voltage gain in dB. For example, this is the frequency response of the first order low pass filter. First order low pass filter means the roll off rate will be minus 20 dB per decade. And for second order low pass filter, the roll off rate is minus 40 dB per decade. For third order low pass filter, the roll off rate is minus 60 dB per decade. For fourth order filter, the roll off rate will be minus 80 dB per decade. So here, what we are saying, as the order of the filter is increasing, you can see that the stop band response is approaching the ideal response. You can see that, because the ideal response of low pass filter is this one. Now just compare the practical and ideal response. As the order of the filter is increasing, the stop band response is also approaching the ideal response, stop band response. That is that we can say advantage of higher order filters. But to design higher order filters, the circuit complexity will be there, because we need more components to design higher order filters. So in this class, I have discussed about active and passive filters, advantages of active filters over passive filters. There are two main advantages. First one is gain is high. It provides gain, and second one is there is no loading effect. After that, I have discussed the frequency response of different active filters like low pass, high pass, band pass and band reject filters. This is the reference. Thank you.